So we want to basically minimize, of course, the distance between the predicted, output target scores. And here, for example, for regression, the ground truth one. So we have the same loss, but the transformation here would be a bit different. So here, this is a simple machine learning model. And what we want to do is to model or to create a graph that encodes the similarity between different nodes. And this will be encoded or represented by the graph, the data graph adjacency matrix, okay? Adjacency matrix. So now in this matrix, I want you to think about this sample. This sample could be anything. It could be a video, it could be an image, okay? It could be text. So you can have your node denoting a particular sample, but you can also have your whole graph as a sample. And we'll discuss, we'll go over different examples in the next lecture, but here I want you guys to keep in mind that your whole graph could be your sample, but also a node in your graph could be your sample. Okay, so these are different representations. So for example, if you're working on classifying molecules, right? So you can say, or brain graphs. So a brain graph, which is a mapping of the brain connectivity between different anatomical regions. So you encode the whole brain as a graph. And what you want to do, you want to know if this graph is, for example, healthy or has a particular disease. Okay, so this is a problem where we're kind of classifying a whole graph. So there are different ways of doing this, but what I wanted to keep in mind that now we are using a graph, and let's go forward. So let's move forward. So in this example, we want to learn how to represent each node. Okay, so the graph here has an original feature matrix. So we do have an annotated graph. So we have the A and we have the X, which is the data feature matrix. So the nodes are actually annotated, that we have features. So this is our X, okay? We have the adjacency matrix. And our goal is to learn a mapping function or a neural network or transformation F that allows us to map X, the input features, onto a new representation, or to embed them, okay, by using the graph matrix and some parameters to learn. So phi 0 is a mapping function that actually will map, the features from layer 0 to layer 1. Okay, so it will map X onto H1. Here, phi 1 is another transformation or mapping that we want to learn that will allow us to map, H1 onto H2. So basically here, layer 1 onto layer 2. So this is a function that maps, layers onto one another. And you can think about it as the W that we had before here. So it's mapping, one layer onto the other. Okay, so we had also nonlinearity of activation in between, but that's a different, that's another kind of variation. But here, simply put, the idea is that we want to learn an embedding of each of these nodes, okay, but we want to learn them together, not individually. And to do so, we will define a function that takes in the structure, which models the interaction between these nodes, because we need that to do the learning and the modeling of the interactions. And we have here the previous, the hidden nodes learns in the previous layer. Okay, so we feed it into the next one with the adjacency matrix and the updated parameters. Okay, so here at the end of this deep neural network, we are going to get a very powerful representation in layer K, so HK, of all nodes in the graph. So this is a deep sequential node representation learning or embedding, okay? So this is exactly what we do in conventional neural networks, right? So we're trying to learn these embeddings. So here we have H1, and here we have H in the final, a layer L, right? So these are the representations that we're learning. And our goal is to do the same, to learn these representations, but instead of learning them independently, we are learning them constrained or guided by a graph structure A. And if you look at this, so let me just remove this a little bit so you guys can see. So what is constant here? So interesting to note that A doesn't change, right? It is actually fixed. And here, these guys, I'm going to use a different color. So X is also fixed. These guys right here and these, the mappings are actually learnable. So we want to learn the representations and we want to learn the transformations. All right. So this is, simply put, as we do that, as we update, like as we train the network, you will see that the loss of this network will start off with something, which is a regression loss. So if we have, the input here, the number of iterations, and we plot L of W, and at the beginning you have a very large loss, but somehow at some point you're going to kind of stabilize your loss and have a very low loss. And this is by, like training your model. Okay, cool. So this, towards the end, as we iterate after a certain number of iterations or epochs, you will see that this final representation is actually very powerful. So somehow we're learning how to improve this by optimizing our loss function. Now, if I ask you, all right, somehow is this supervised? So in this case, we will see an example of classification in a bit, but definitely we can learn this in a supervised way, which means, my loss right here will impact the learning of all these, all these hyperparameters, the phi's and the h's. All right. So yeah, so that's a very simple, that's the key idea here, is to learn how to embed and deeply embed sequentially using a structured matrix. So let's look, let's go deeper and try to understand this fundamentally, all right? So we have a vanilla GCN layer right here. So the vanilla GCN layer will perform a very similar operation to a simple deep neural network. But let's look at what deep neural network does. So we have an input training sample here, xi. Okay, so xi will be the input, and then we're going to pass it. We're going to transform it through multiple basically transformations that we're going to learn. So this transformation maps this basically xi, the input, onto the next space. All right, and then we apply an activation for introducing nonlinearity if we have any nonlinear relationship or complexity in the data. So this allows us to capture nonlinearity. Okay, capture nonlinearity. Yeah, so we continue to repeat that multiple times, and then we're going to have WL here transpose, and you have WL plus 1. And this is the mapping function of the whole network. Okay, so towards the very end, after we calculate all of this, and you can see that it's a long calculation, and that's why neural networks are heavy, because this kind of requires the optimization and the calculus of the gradient of the loss with respect to all these hyperparameters, all these matrices, the W1 to WL plus 1. Okay, and towards the very end, after you calculate, you're gonna get your yi hat, which is the predicted score. It could be something, I don't know, like 0.12. All right, cool. Now, the final layer is a linear aggregation layer. So it kind of aggregates the features that we learned. So, if you look at this whole block will get us actually the final HK, the final so here it's L, because it's the final representation in layer L. So these are the node embeddings in layer L. And now we're going to aggregate them using this final mapping, that allows us to do the prediction of, to map it onto a single value, to do the prediction of the score. This is done individualistically, so which means for each point independently. Now, let's look at the generalization of this simple mapping function or mapping network, deep neural network, to graphs. Okay, so we're going to draw analogies. So in this example here, we have an input graph G. So this is, in this second part, we'll cover the graph mapping or embedding through a graph neural network, in particular, a GCN, okay, a simple GCN. And here we have our graph, so composed of nodes and set of edges. And we can also, if you want, we can sometimes, in some notations, we add the A here, which is the adjacency matrix, okay? So this graph is an annotated graph, which means each node, all right, each node is represented by a feature vector. So it's actually this way, because these are the number of features. So this is actually the feature vector assigned to this node, all right? So now let's call it node I, node I. So what we have as input to this graph neural network is two things. We have the A, and we have the adjacency matrix of the graph and the feature matrix of the graph. So this is the feature matrix. So the feature matrix has dimension d times n. N is the number of samples. And what we do, we feed this graph into a graph neural network. So that basically takes in the input features and it applies this operation. So I'll explain this in a bit. So we have first, this mini operation here, which is, multiplying the X by the A, okay? And then we multiply the output by the transformation that we want to learn, which is the omega 0 here. So the omega 0, you can think about it as what we called earlier the W. This is the transformation. And we apply the same thing. We apply an A right here, the activation. So if you guys look mathematically, what's the difference between the top block? So that's, let me use a big, like this one. So what's the difference between this block and this one? So this has basically an activation. We have an activation and we have the learned mappings here, omega, and then the X, all right, the feature matrix, the input features, right? And then we have additionally an A. So that's the difference. So now we're constraining our aggregation and transformation by the graph structure, all right? So if we repeat that, so we'll dichotomize this in a bit. So we'll go over this in a bit in detail. But the idea here is that we have, this first transformation that we apply. And as we apply, So as we apply this transformation, we're going to get the node embedding. So these are the node embeddings, okay, of the whole graph. So we will update these. These are the node embeddings for layer 1. So this is the first layer. And then we repeat that again. Now we take the node embeddings, output it here, okay? So these are the node embeddings of this layer, and we feed them into our mapping function, and the A is fixed. And we transform through the omega 1. So omega is actually what is learnable. So we're trying to learn this quantity, this transformation. And we do that again. So we're going to get the embedding of layer 2. And then we repeat that until we get, for example, here we have only 3 layers. So we repeated that 3 times. So now if you guys know this, we have an A hat here. So what is A hat? Actually, A hat is the original matrix, A plus identity. And this is, we added identity here. So we wanted to kind of make sure that the output of a node in a hidden layer will depend on itself and its neighbors. So if the node is not self-connected, so if we have a node like this and it's connected to many other nodes, if the node is not self-connected, we cannot update its embedding, okay, its own embedding. So we need to take into account the node self-connectivity to be able to update its embedding right here. So to do that, we need to make sure that the adjacency matrix has ones on the diagonal, it has some self-connectivity there. Okay, so that's why we call it A hat, and A hat is A plus identity, it allows us to do the update, of the node embedding based on its self-connectivity. All right, so that's important. Now let's look at this. So what's actually going on here? What is this, vanilla network doing? So first, we call this the propagation rule of the network. We call it also the message passing rule from a node to other nodes in the network, okay? So it's a message passing rule. So in this rule, first, we do what we call an aggregation. So basically multiplying the embedding by the A. Remember, guys, when we had the first lecture, we talked about A, multiplication by a vector X, as an aggregation or integration operation, okay? So basically what happens is that if you take the A matrix right here, and this A, you take the node I, and you have, let's say, this type of connectivity. So this connectivity pattern with all of its neighboring nodes here and nodes. And if you multiply this by H, okay, so let's say the embedding of node I by a particular, so the embedding of I, for example, okay? So what we're gonna do, we're going to update the embedding of I based on its neighbors. So we're going to only integrate information or take information from these neighbors. So this is actually an integration process. So here, integrate over neighborhood, integration over neighbors of I, node I. So in this case here, the first one is what we call a feature aggregation or integration. So this allows us to aggregate the features from all neighboring nodes. And after you do that, the second part right here, after you aggregate the features, you transform them. So the second part is a feature transformation through the learned weights. So now we're mapping onto a new space. So we're taking, okay, so we can do it this way. We're taking this and we're passing it through the omega to get a new representation or a new embedding. And this is transforming from one space to another, or one representation of another or to another. And the final part here, A, is actually the nonlinearity. And this is where we introduce the, the nonlinear activation function. So we apply this to this whole output, to this whole block right here, to every single element. We apply the activation that we have. For example, if you use a ReLU, this is max 0x. It's a function that looks like this. So it's an activation function where you have 0, any positive value. So let me do it this way. So any positive value will be kept, okay? And if you have negative values, it will be set to 0. So this is max 0x. It's one type of the activation, neural activation functions. So now what happens is that you can see that through this A, we're doing aggregation through neighborhood, which means every time, okay, so let's look at this together a little bit. So every time I'm taking this embedding, right, I'm going to update it based on my neighbors. So I will aggregate these embeddings right here. So the first aggregation is kind of summing them up. So I'll add them up through this first block, okay, and also take into account the self connection right here, the self embedding. And after we sum them up, so after we add them up somehow, like we get to transform them through omega k. Okay, so you imagine that you're taking the average of these guys, all right, and then you're mapping them through omega k, and then you're taking the self connectivity also and mapping the self connectivity of, or the embedding of this node, all right, through self connectivity. So now let's try to look at this in a very simple way. So if we remove the nonlinearity, so here we have the nonlinearity, okay, so the A here. If we try to remove the A, what happens? So let's look at that. So here I'm going to remove all of this. So we have our nice, mapping network, and we're gonna write the equation. So let's take a minute to write this recursive update of the network embeddings from layer to layer. So here we start with layer H1. H1 takes H0. You know, guys, that H0 is actually initialized as X, the original features that are on our graph. So right here, so these are the original features, okay? And then we will see how are we going to embed them. So we want to project this feature node xi towards a space, you know, where we go from RD to same thing, RD prime. But now when learning this embedding, when encoding these features, we want to take into account the structure of the graph, okay? So let's take a minute and try to kind of write this down, update rule. And I want you to substitute. So every time you're going to kind of write these, replace, you know, the value. So for example, let me start here. So H2 is equal to A hat H1 omega 1. And then you're going to substitute. So here, replace it with this and see which kind of formula we will discover over there. All right. So if we propagate this forward, you will see that we will discover a very nice formula here. So basically H2 is equal to A hat squared. And then you have, we have H0, which is X. So I'm going to replace it with X. Okay. And omega 0, omega 1. So these are two composed transformations. Okay. So if we propagate that, transformations. So let's try to write down the generalized formula. So we're going to have H K plus 1. So here, put it down here. It's not squared. So it's going to be A hat raised to the power of K plus 1 times X times omega 0, the transformation, omega 1, until we get to omega K, the mapping from layer K to K plus 1. So here, if we write this down, this is, you know, mapping from K to K plus 1. And here 0 to 1, 1 to 2, etc. And this is the final composed transformation. Okay, so we can call this actually omega total. Okay, so this is the final transformation that we want to apply. So we, as you guys can see, the final, if we're going to get to the final layer, it depends on multiple operations, multiplications. We put in the input feature, the original feature matrix X. So this is our input feature matrix, right? And then we take the adjacency matrix and we raise it to the power of K plus 1. And this defines the embedding of the nodes, the node embeddings for you know, each node in the graph. So the embeddings of each node in the graph, okay? So what does that mean? So now we have seen the two things here. So we have seen before the power of matrix multiplication to integrate information, and we see information integration here from the local neighbors, right? And we have seen also, so this is the integration, the first part, okay? And then we have seen the transformation. And as the network gets deeper, then we can post-transformation, we kind of concatenate or stack these transformations, and we raise a to the power of K plus 1. So what is a to the power of K plus 1? So let's look at that together. So this is a reminder from the previous lectures. So if you take a matrix A, and you raise it to the power of K or K plus 1 here, so it means that for each node I, this matrix will store the total number of walks of length K plus 1 from node I to node J in the graph. Okay, so it gives us the number of walks from A to J in the graph. So in this example, so let me have here number of walks, and if we have a graph like this, so it tells us that actually how many walks of length, for example, 2, we have from this node, from node for each node I. It stores the total number of walks from node I to j. Okay, so this is node I and this is node j. This is I, and here let's put this is j. And if we do a to the power of 2, so the number of walks of length 2 from I to j is actually 0. We don't have any walks. But if we do a to the power of 3, we have 1 here. Okay, and we have another one here, 1, 2, 3. So we have 2 walks actually. All right, so that's what it means. So we're going basically from, it tells us that I can reach if I start from I can reach j within 2 hops. So the power here, this power matrix, it actually explores the neighbors that are k+1 hops away from the original node. So which means that this is a very important observation, because if we take h1, so if we take, the first, let's say here, the first ring of neighborhoods, so to get h1, and the first layer of the network, we are exploring the one hop ring neighborhood. So we're exploring the immediate neighbors, all right? And then when we get to the second layer, because we're raising it to the power of 2, right? So we have a2 in the second layer for calculating h2, right? So it depends on a to the power of 2, etc., etc. So this means that we need to do 2 hops, right? So in this case, we're exploring further neighbors. So a neighbor of a neighbor that is 2 hop away. So we're exploring this green 2 hop neighborhood. So this green ring right here. So if I use maybe a different color, and let's see if we can do that better. All right, so this neighborhood right here. Okay, so in this case, you guys notice that this matrix, this formula, this update formula tells us nicely what is happening in a GCN layer. So as you go deeper, you're actually exploring a neighbor of a neighbor of a neighbor until you get to the kth, layer, where you're getting, to the kth ring. All right. So every time you apply a neural network here, you're actually moving, from a neighbor to a neighbor, and you're exploring further away, I would say further away points or nodes from each node in the graph. So you're expanding the neighborhood. So here, deeper means neighborhood expansion, okay, using a graph. And we can see that actually, so here, in this example, this defines what we call the receptive field of a graph. So the receptive field, it means how many nodes will influence the learning of my embedding at a particular, my final embedding. And in this case, we have, the k+1 here. It means that the k+1 ring will actually influence the final, embeddings that we're going to get. So the receptive field of my graph neural network is the maximum information I'm getting by, traversing the graph from a particular node. And basically, that's the final layer and the final k-hop ring. Okay, so here is the k+1 hop ring. The ring of neighborhood defines the receptive field of the graph convolutional network. All right, cool. So as you guys see, with this very beautiful mathematical operation, if we think about it for a minute, so the deeper we go, it means the further we expand the neighborhood, okay? And the larger my receptive field becomes. And of course, we have more computational load because we need to calculate powers of matrices and multiplication of matrices. But that allows us to kind of get representation of this node as a function, not only of its in immediate neighbors, but as a function of its neighbors of neighbors of neighbors across several neighborhood rings. And this is why, you know, this is how we get deep in a neural, in a graph neural network, okay? And this is the meaning also of the layers. So now there is one important thing. So we talked about this. Now you can see the difference between a simple neural network operation like an MLP, multi-layer perceptron, or a simple fully connected network, and the graph mapping through a graph neural network. So this is a vanilla GCN, and we saw the case where we removed the linearity. So actually here we have linearized the network by removing the nonlinearity, and we discovered that this depends on powers of matrices and walks on graphs. All right, cool. Now I have a question here, which is important. So can we map any node with any neighborhood size? So can we map any node? Can we create an embedding of any node of any neighborhood size? And you can look at this example. So in this example, this node has two neighbors, all right? So it has two neighbors, and this node has only one neighbor, all right? Still, something really exciting, and that we will see also in the next lecture about graph neural networks, is that yes, we can. We can, learn a universal transformation, okay, that allows us to update the embedding of any node in the network and of any kind of neighborhood size. So this kind of transformation or layer update, it does not depend on the number of neighbors you have, because, and this is thanks to the aggregation rule. It's thanks to this, operation that we're doing, because first, if you have, three neighbors, you're going to aggregate these three neighbors into one, and then take the embedding here and you add them up, and then you transform. If you have, for example, two neighbors, you're going to do the same. So you will take, these two embeddings, add them up, get an average, and then add that to the embedding of this node. And in this way, you get the final embedding. So you get the final updated embedding for this particular node, okay? So nicely, this does not depend on the number of neighbors. And this is something really powerful about graph neural networks, because it generalizes across different neighborhoods, which means I'm learning an embedding function, omega total here, that allows me to kind of, that works on any node in the graph independently of its, local topology. All right, cool. Now, one last point in this session, so is that I want to cover the importance of the layer-wise normalization and propagation rule. So here, this is the generalized propagation rule that we discovered. So this is basically, we want to learn an F mapping. The F will be parameterized by, for example, omega, let's say here, K, all right? So in this case, we have set the transformation to learn. These are the transformation parameters, okay, to learn. And we have here the input, the embedding learned from the previous layer, and the adjacency matrix, which is fixed, okay? So this is our general propagation rule. And one thing important about this, is that the A is fixed, all right? So A is fixed, which means I'm hypothesizing that my network is robust and reliable from the beginning. But let's say these two nodes actually should be connected, but because of my, like the way I constructed the graph, they were disconnected. So somehow, my results depend on the reliability of A. If A is not, it has noise, or it has outliers, or it has mistakes, then this will mess up the whole propagation rule. It will mess up the whole propagation process, okay? So one thing you may consider is that, well, maybe we need to kind of learn how to fix the A, or maybe we should not, you know, fix it during the learning process. Maybe we can make it learnable. So there are a few papers on this, like recent papers, but the original GCN models, they assume that A is fixed, and we kind of diffuse information, you know, from neighboring nodes, or diffuse embeddings from neighboring nodes to the current node. And that's how, you know, like we're doing the aggregation along a fixed structure. So in the next round, or in the next iteration, we will not have a change of topology. The topology will be preserved. All right. So this is a strong assumption to make, and it's a questionable assumption that we can, of course, you know, revisit. But yeah, so this is the generalized propagation rule. Now let's talk about the layer-wise normalization. So now, in this formula, we have updated the A hat. So the A hat is multiplied by D hat, the inverse of D hat. All right. So D hat is actually the degree of the node degree of all nodes that we have in A hat. Okay, so you calculate the node degree of each node. And here, let's say we have here the D hat, and then you create the inverse D hat minus 1. So if you have, for example, here 2, you're going to have half here, okay? So 4, 1 by 4, etc. So you're inverting the degree matrix, and this matrix tells us that it has zeros, okay, off diagonal, and on the diagonal, it quantifies the strength or the degree of each node. So if you have a node which has 2 neighbors, then the degree is 2. If it has 4 neighbors, then the degree is 4, etc. So each node will have a particular degree, and we want to store the strength of each node here. So this is the strength of each node. So the goal of normalization, that when we want to do information diffusion, we want to be careful, because look, if this node has so many neighbors, we will aggregate so many values, but we will not divide by the number of nodes, which is here, you know, 5. We will not normalize. So this will be skewed or kind of biased towards the nodes that have many, many neighbors, oppositely to a node that has only one, you know, neighbor, right? So this node has one neighbor. So in this case, you know, the aggregation here, the aggregation of information will be biased towards the node of the highest number of neighbors. So why this is a problem? Because when you have the final embedding here of the node, you look at the embedding of, this is called Z strong, node strong, and this is Z weak, okay? So when you compare the Z strong, okay, with the Z weak, what happens when you pass them through the activation, okay? So the activation function will look at the distribution of these and will keep the highest values. The problem is that this vector has so many high values, and this one has smaller values. So when you activate these, this signal, this node right here, will not count anymore in the activation. So it will be kind of repressed, okay? So it will be repressed. The values will be small, so it will be negligible. It will have a negligible, you know, kind of embedding, right? So which is something we don't want to have, because this node may be actually very important, and we still do want maybe to classify it if we do node-based classification. So we need to normalize with respect to the size of the neighborhood. So we need to divide by the size of the neighborhood, and this is what we're doing here. So we're dividing by the size of the neighborhood. We're taking the A, we'll dividing each element of the A by these, you know, by the strength of each node, the overall, the average strength of each node, quantified here by the degree. And that allows us to normalize and to get, you know, to learn embeddings that are not skewed or biased towards, you know, well-connected nodes. All right. So then we can compare easily and we can learn coherently. And this normalization is vital. So you guys can also try this You can try to train a GCN using the simple propagation rule without normalization. So you remove the D, right? And then you look at your results. If you're doing classification, if you're investigating or examining accuracy, sensitivity, specificity, and then you can add the D back, you can normalize and see whether you get better results. So this is what we call a normalized propagation rule, and it has fixed the problem that we had earlier of without normalization. So it actually controls the embedding variance between also layers. So, so this is also very important because it allows us to suppress the gradient explosion and vanishing phenomenon. What does that mean? It means that when we go from layer K to K plus 1, from neighborhood K to neighborhood K plus 1, right? So in this case, you have the distribution of this matrix, okay? So maybe it looks like this. So if you don't normalize, the distribution will be very will vary a lot between two consecutive layers. So you may end up with completely different distributions, and this is, you know, something that you don't want to have because of lack of normalization. All right, because when you have large variance, okay, when your network jumps, it goes, for example, from a distribution like this of node embeddings. If you plot the histogram of this matrix and the histogram of this matrix, and you have something like this, right? So this is not good because the network will struggle to learn. Remember, the goal of neural network is to learn this kind of, you know, manifold that I lost track. So to learn a manifold that goes from, you know, that creates smoother spaces, subspaces, through these mappings or consecutive sequential mappings, right? So if you're making jumps, it's not good because you're not smoothly somehow creating a nice space. You're creating these jumps and you're learning from space to space, and that will not allow you to learn well, that consistently, at least across samples. So you need to kind of control the variance of the embeddings between layers. And this is a very important problem even in deep learning. So how to kind of make sure that the distribution of your hidden embeddings or the latent representation in layer K, K plus 1 are not very different. Of course, you want them to be different enough to not learn exactly the same thing, but you don't want them to be, you know, shifted away, all right? So this embedding normalization, it maintains the scale of the output feature vectors, and it's something kind of good to have. All right, cool. Good, so this was a brief introduction into a vanilla GCN layer. And now in the last part, next, we're gonna look at final examples, introducing the biases and, you know, more nonlinearity and rewriting that properly with all these beautiful matrix multiplications and using linear algebra. And then we're gonna look at last at a simple graph classification task. And that will wrap up this